Yeah, next. Cool. So I think welcome you all. And I think this just want to announce that there is this RecSys challenge, which is jointly organized by ACM and ShareChat, which is open. And the last date of submission is 18th June 2023. Below is the link to the challenge page. Yeah, Sarang, next slide. So, sorry. So for today's agenda, so I will start the session with a brief context setting, followed by we have an talk by external speaker Ayush Mudgal from Pinterest ads. So who would talk about what are the challenges that happens in offline conversion prediction. Then we will have a small break, bio break, and then we will go into 3 talks from ShareChat from Kushal, Chirag, and Shubham. They sort of talk about different aspects of Kushal will be talking about how do you build an end-to-end recommendation system. Chirag will look on multitask learning, which is sort of very pertinent to our problem statement. And Shubham will actually talk about different aspects of features in ad recommendation system and what are the challenges. Now, one interesting thing is that we will have a Q&A session after that. And what we have done is that to incentivize people asking good questions, the top questions will win Amazon vouchers. There are top 3 questions that will win Amazon vouchers. So just stay back and ask and win all these things with you. Sarang, next slide. Okay, so I think I will take not much time. I will just talk about 10 minutes. So this is quickly start up into what's about ShareChat and Moj. So we are a Indian social network company, and which has we are based off 2 what we call apps, which are called ShareChat and Moj. While ShareChat is our first app, Moj is short video app platform that we have built. We have close to 180 million active users on ShareChat and 160 million active users on Moj. We sort of have a very rich community of creators, close to 32 plus million creators on ShareChat and 50 million plus creators on Moj. Now, in terms of interaction that our community does with the content, we have approximately 75 million plus UGC content generated on ShareChat every month, and that number is around 100 million for Moj. And in terms of shares that happens on our platform from ShareChat, this is 2.5 billion and 4.5 billion video plays per day on Moj. So all in all, it's a very sizable community that we are talking about, a very vibrant user community that we're talking about. Sarang, please go next slide. So in this context of community, right, there are a few diverse things which I want to clearly highlight out. So one of the things that is happening is that this social network is as diverse as 18 plus languages. And this is very diverse in the sense that it's not that one language is commanding everything, or they're Hindi, Tamil, Telugu, these are various languages in India, and they're have equal representation, or more or less equal representation. So what it means is a multilingual setup that we're talking about. We have users spread over a huge geographic area. So people who understand India, they understand that how diverse that setup could be. It's huge geographical area. It has different aspects, different diversity with respect to languages, cultures, technology, different usage patterns, and so on. One of the key characteristics of our platform is hyperlocal content. So we are not a social network in the sense that you get updates from your friends. We are not popularity content where you get top 1% content, but we're getting a very local generated, local in your language around you, a very hyperlocal kind of content. One of the key aspects for our platform is that we have a big population which may not be conversant with written, they are literate, but they're not very well conversant with, say, writing or written communication. So video has emerged as a very convenient communication medium. So it's very surprising that in India, where people might not have been generating lot of written content, but when it comes to videos, we are surpassing everything. So and this content is not being generated by only tier 1 users or so. It is the penetration of content generation has gone to tier 2, tier 3, and so on. With this mix, there is one very interesting aspect that has happened in India is that we are mobile enabled country. We do massive amount of mobile payments. We don't do credit card payments, but we do massive amount of mobile payment thanks to the QR code. Now today, you can actually buy a tea in India in the remotest corner through Paytms and UPIs and so on. So that's a very good mix back into the way we want to monetize our platform. And finally, like this audience is very price sensitive. So if you think about all these audience characteristics, there are key things which is diverse. It is like hyper local. It is like video centric. It has mobile payment, but not a conventional mobile payment, and a very price sensitive audience. Yeah. Sarang, can you go next? So in this context, we just want to talk about briefly about ShareChat ads. So we are like 150 plus team of AI engineering and product. We support multiple monetization models. So we have branding, we have influencer marketing, we have sponsored content, we have like within video ads, we have like sponsored filters. We had like where you can actually have a filter on Moj and that could be sponsored. We have creators can promote their posts. We have conventional image ads and video ads. In terms of problems, we do have a lot of problems in terms of the standard computational advertising problem. We are at an intersection of deep learning, auctions, portfolio management, adversarial systems, delayed feedback, and so on. So pretty interesting piece of pretty interesting place of work for if you're excited by any of these areas. Sarang, can you go next slide? Cool. So with this, we come back to like the ACM ShareChat RecSys challenge. So what is the aim of this challenge? Like this like ACM has this, RecSys is a very well-known conference on recommendation systems, one of the tier 1 conference on recommendation systems to disseminate the latest happenings in terms of in the research of recommendation systems. And one of the aim of RecSys challenges is to actually further the research by providing a diverse set of real world data or problem statements. So in the 2023 version of this challenge, the task that we have posed is that we want to predict install for ads that have been shown on ShareChat and Moj. Now, if you think about this task, right? So the key aspect of this task is that it's a real world data for advertising, number one. Very important part, which is there is that like for both for business reasons and also to further the privacy preserving advertising. So the data is actually anonymized. Like, so the conventional feature vectors of IDs and so on with user IDs and then like hyper local targeting, that is not being captured in this data. This data has been actually user anonymized with all differential privacy added to it. So the idea there is that what can we do with aggregates and what can we do for advertising so that we can actually preserve the privacy of the user. The third thing which is there is that it's a two-stage thing. So you have impression to clicks and then clicks to install. So you have to predict the install that's happening. In terms of attributes, we are talking about user attributes. We're talking about ad attributes. We're talking, we have actually provided interaction features. Briefly talking about data sets, it's like 21 days of training data with 1 day of test data. And we have sampled the data with negative examples being undersampled. Now, this is the basic setup. Now, this sorts of gives us an opportunity to actually work with the data that is being used for actual advertising in ShareChat. And with all these features, like this also gives an opportunity to share what newer research that's happening. Now, with this, I actually want to move on to the introduce my speakers today, fellow speakers today. So we have Ayush Mudgal from Pinterest. We have Kushal from ShareChat. We have Shubham from, again, ShareChat, and we have Chirag from ShareChat. So they're like Ayush, who is from Pinterest, who is going to talk with us. Chirag, Kushal, and Ayush are from ShareChat. So over to you, Ayush. Ayush, I think you're muted if you're speaking.
Oh, thanks for that. Yeah. Okay, I can start again. Yeah. Hi, everyone. Thanks for joining with us today. I'm Ayush, a machine learning engineer at Pinterest. Today, I would be sharing some practical lessons from conversion ranking within Pinterest, some of the recent changes in the privacy landscape, and how it impacts conversion ranking, and some of the industry standard techniques to improve personalization in the space in general. Next slide, please. Yeah, so today I'll start with introducing the Pinterest platform and ads at Pinterest with a special focus on how third-party offsite conversion optimization products works in general. Then we will present some unique challenges to conversion optimization, unlike normal on-site engagement problem of click-through prediction. Then we'll take a small tour into the evolution of ranking models at Pinterest. Next, we will touch upon the recent privacy landscape changes and how it impacts personalization. Lastly, we will deep dive into how ad personalization can still remain effective as the industry evolves to become less reliant on individual third-party data. Next slide, please. Yeah, to give a brief overview, like Pinterest is a platform to find inspiration and tools to realize that in one's life, people come to Pinterest to find inspiration in all forms, be it on what to eat during dinner to planning their next vacation. This is what a user generally sees when they land on Pinterest when they open the page. This is the home feed in general. It shows recommendation pins to users based on their interest and past engagements in general. So home feed here shows different recipes and dog training ideas for my dog. Now let's understand how the user interacts with this platform in general. Next slide, please. So this is like, let's say like today I want to decide what I want to cook in general. So let's say I search for paneer recipes on the platform. And then when I click on the search button, I'm shown a personalized curation of recipes all tuned to my interest. And I might decide to interact with content based on their interest. Let's say I like paneer 65 in this case, and I click on it to explore it further. Next slide, please. So now as I click on the pin, I see like some details about the recipes and the steps to prepare the same, and also along with suggestions of some similar items. So Pinterest is a rich visual catalog in general. And by going through this content, let's say the user likes and wants to save it for future reference, they can go and save it to their collection of boards in general. So this was an example of how typical user journey on the platform looks like. So more than 400 million pinners like me come to Pinterest monthly to find inspiration, to create a life they love, and find the platform to be filled with positivity. Pinners all over the world have saved about 330 billion pins in more than 7 billion boards, encompassing more than 35 languages in general. Next slide, please. Ads at Pinterest help connect advertisers or partners with pinners to bring inspiration to action. Imagine a user is in a purchase journey to remodel a house. It allows merchants in the domain to connect efficiently to these pinners and bring them inspiration to do the actions. Next slide, please. So in this particular talk, we will be mostly discussing about the conversion product. So here's a brief summary of ads product provided by Pinterest. At Pinterest, our goal is to build a platform that brings users inspiration to realization. For this, Pinterest provides a performance ads platform, which is strongly powered by conversion business. As downstream funnel events, like conversions are downstream funnel events which the advertisers mostly care about in general. These are the advertisers' objectives in general. And one thing to highlight, like unlike other on-site activities or products in general, like conversion products directly link to the impact that the advertiser is aligning for in general. One thing to highlight here, unlike general click-through ad products, where billable events are clicks in general, for conversion ads, even though we optimize for downstream conversion events happening outside the platform on the advertiser side, the billable events is still impression, which means advertisers are charged whenever a pinner views the ads on Pinterest. This brings in extra challenges to ensure that the conversion prediction is accurate and that we don't overcharge or undercharge our partners. It is very important for a well-functioning ads marketplace to have a stronger personalization so that we can meet both our partner and pinner needs. So going forward, we will discuss how we make the ads more personalized for the users in general. Next slide, please. Here we show a very high-level data flow for a conversion optimization product. After an advertiser creates an ad through our ads manager system, the ad passes through a series of security checks, and once successful, the ad is indexed into the system and is made available to be shown to pinners through our ads delivery system. At the ranking stage, the conversion model predicts the likelihood of conversion given the context coming from the user. The winner ads are then served to the pinner, which they can engage with on the platform, as shown in number 3. Some of these user engagements, as the user engages with the platform, could contribute to users converting behavior in general, such as checkout, sign up, or adding it to their cart on the advertiser domain. As the pinner interacts offsite, Pinterest receives data from the advertiser domain. Some of this data is sent back to Pinterest's measurement system, which will log and try to match and attribute this data to a pinner's activity on Pinterest if possible. This in turn acts as the training data for conversion model, which fuels to improve the accuracy of the prediction. Next slide, please. There are two important concepts to understand conversion optimization campaign in general. First is the conversion event. It is the type of event that happens on the partner website when a user interacts there. We currently support 4 conversion types to choose from and optimize against, mainly checkout, sign up, add to cart, and lead forms. So whenever a user does any of these activities in general, the advertiser sends back the data to Pinterest servers in general. The second important concept is the attribution window, which refers to the time during which Pinterest can take credit for a conversion event. For example, a 7771 window means that Pinterest can take credit for any conversion on any device of the user that happens up to 7 days after a click, or sometimes past a save on the platform, or 1 day after the pinner views the ads in general. So depending on the advertiser's objective, they can choose what kind of conversion event they want to optimize for and what kind of attribution window fits their budgets and needs. Next slide, please. This is a very high-level overview of a general ads delivery funnel. Whenever a user visits the platform, there's a request to show relevant content, which includes ads to the pinner. To enable efficient, low latency, and personalized recommendations, ads delivery systems are typically broken into 3 components. A targeting and retrieval system, which focuses on maximizing recall and reducing the search space. A ranking system, which focuses on providing precise predictions to power your auctions. The auction combines numerous business logics to balance advertiser needs with pinner use case to deliver the best possible content. Today in this talk, we will mostly focus on the ranking optimization problem, which is typically a binary classification problem. And more specifically, we'll focus in the context of conversion optimization and go into details about some of the practical lessons from our journey. Next slide, please. For conversion optimization, this problem basically boils down to predicting conversion probability given an impression. Briefly speaking, we currently support 2 categories of conversions based on the attribution type: click attributed conversions and view attributed conversions. Click attributed conversions refers to a conversion event that happens after a user clicks on the content at Pinterest. This event is normally more valued as the user had a direct measurable engagement with the content on the platform. To model this, we break it into two different components. To model it in the impression space, we break it into 2 different components given by probability of click-through rate, which is probability of click given an impression, multiplied by probability of click attributed conversion given a click. While here we also consider and model jointly conversions that can happen beyond 1 day. So if you can imagine specifically for conversion predictions, a user might interact with an ad on the platform today. They might not purchase directly. They might be still in their purchase journey, but maybe they buy it after, let's say, a day or 2. So there's a trade-off of data freshness and model accuracy here. However, there could also be conversions where the user never interacted or clicked on the ad on Pinterest in general, but they might have viewed the ad in general. These are less causal, but can happen without any engagement. We model this component directly on the impression level. So impression refers to an event when a user sees an ad on the platform for at least X seconds in general. We also multitask learn across different objectives such as checkout and add to cart and different attribution windows in general, both from a model maintenance perspective and to improve performance. Chirag from ShareChat would be sharing more details into multitask learning later in the workshop session today. So please stay tuned to learn more deeper insight into it. Next slide, please. So I think we'll share some of the challenges which are unique to conversion modeling in general, unlike click-through rate predictions. Unlike click-through rate models, the labels for conversion models are controlled by advertisers. And thus, they have greater noise due to the stochastic nature of the measurement process. Advertisers can easily abuse the conversion events, and that brings challenges to modeling it effectively. As the quality is not maintained by Pinterest, we typically have seen several times that abnormal amount of conversions are sent to our pipelines, which might break the systems in general. Another challenge that stems out from the fact that conversion events are low funnel events and extremely sparse in orders of magnitude. For illustration, the trend on the right depicts the typical scale of conversion volumes. For every 10,000 impressions, there might be only 100 clicks, which in turn could only lead to, let's say, one conversion event. So this put extra constraint on the model complexity and makes the A/B experimentation iteration slower. The third major challenge comes from the delayed feedback. So if you can imagine that like a positive label is sparse, but this positive label can still happen like multiple days after the user interacts on the platform. And this comes from the attribution window in general. This means that complete labels are only available once the attribution window closes. This naturally introduces a trade-off between model freshness and update frequency. To account for this, we currently utilize a combination of fresh models trained with one-day attribution window and another models that model this delayed feedback in general. Next slide, please. Yeah. So let's go over a little more details of challenges due to data quality and some practical lessons from the same. Conversions could be sent through incorrect types. For example, advertisers might incorrectly send checkout events when the user visits the page. This can easily result in flooding of labels being reported for this advertiser. This abnormal data can have effect both on model training quality and also on experimentation metrics. Based on the use case, different measures need to be taken. For example, it might still be okay to report these conversions to the advertisers. As advertisers are reporting these events, they would expect to see similar volumes. But this might not work for training models in general or understanding typical A/B experiment metrics. To identify such issues, we have a combination of human-in-the-loop process and algorithmic approaches to filter such abnormal outlier data in general, and apply this removal based on use cases and requirements in general. One of the things to note here is that one advertiser might send abnormal data. What we want to also control is the impact of wrong data from one advertiser should not impact the performance for another advertiser in general. To incorporate this, we normally use ID-based features in the model in general. Next slide, please. There are usually two ways to handle the label sparsity and data volume challenge in general. One aspect is to enhance data and leverage multitask learning methods to learn from other tasks and denser objectives. The other aspect is to improve model efficiency given the data volume. This can happen roughly through two ways. One, through efficient architectures, better feature crossing and learning across features, and developing strong and performance features, especially around user side and user advertisers interaction. Stay tuned to learn more about feature engineering from Shubham today, who is scheduled for a session later. Next slide, please. The following shows the evolution of model architecture for Pinterest ads, which is very typical with recommender systems as they mature and progress towards more complex architectures and feature usage. Pinterest ads started with simple logistic regression models in 2014, moving towards adding nonlinearities through a fusion of gradient boosted trees and logistic regression, and then to fusing deep neural networks with decision trees in general in 2018. Further improvements happened through advancements to multitask learning and later utilizing more real-time raw sequence of user recent engagements to attention modules and transformers in general. Next slide, please. Sorry. The following shows a very high-level overview of the major components of our ranking model. This follows very closely with Google's implementation of deep and cross networks. The main focus here is to automate the feature transformation process as much as possible. The representation layer implements many pre-processing modules based on feature distributions before they are fed into the model. Summarization layer serves as a layer to learn explicit feature grouping based on prior intuitions. This allows to embed features into a common embedding space before feeding them further into the network. Latent cross layers are designed to learn high-degree feature interactions between features. I'll cover briefly in a later slide. Later, these are passed through fully connected layers and optimized for binary classification task at hand in general. And please check out our Medium blog for more details. Yeah, next slide, please. So this is like, in this slide, like from the architecture shown above, we can now extend it to perform like multitask learning. We can leverage the shared feature presentation bottom layers across different objectives and optimize for multiple objectives of interest. To enable complex models, we utilize a simple architecture parser, which can control which parameters are shared across which components. This enables to give controlled sharedness and business objectives, and provide different sampling techniques per tower. Next slide, please. The following shows a very 100-foot overview of the production convergent model at Pinterest. To address label sparsity issue, we utilize a combination of dense on-site signals like click, good click that happen on the platform. This helps to enrich the training data and also help to warm start the shared parameter space from rich signals in general. This enables to learn more efficiently than just learning the task independently. So from here, we see that when we learn the network in a multitask fashion, we can see significant gains coming in versus independent models in general. The click-through attributed convergence in this diagram is trained only on click data and leverages multitask learning from all of the other auxiliary tasks. We can use impression data to learn the embedding and benefit click-based tasks to the shared bottom. We also add more auxiliary tasks like good click, which are more correlated with convergent tasks. For example, during the journey of a user conversion, there are many other actions along the way apart from clicks that the user performs. For example, a good signal is if did the user spend more than X seconds after the click on the website, which is typically the process before someone purchases anything, before finalizing their purchases. The auxiliary heads are only utilized to aid the training process and are not used during the serving time. This architecture setup allows us to co-train multiple similar objectives like checkout and add to cart and different attribution windows together, also in the same model, which reduces the number of models to maintain and also improves developer velocity along the way. We share the offline results of the change in our system in general, which led to significant changes in the online setting. Here, also for feature crossing, we can replace it with more efficient versions from like Google's TCN v2 or more recently transformer-based crossing methods in general. Next slide, please. Yeah, features are important fuel to boost model performance. User level and interaction features greatly improve personalization because they can help to rank different content in general. While item level features help to provide the right matching, below we are sharing some of the lessons from our feature engineering efforts in general. Prior engagement rates are important signals to guide the model to predict around the expected range. Rich graph-based features help to capture semantic information. Pinterest in general has been forefront of graph-based technology. Please do check out our work on the same link here. Advertiser side features are other important features which help to identify advertisers with higher quality of content which matches with the provided images on the platform. User behavior modeling is crucial for understanding user behavior both through their long-term sequences and also real-time in-session sequences. ID features such as advertiser ID, ad group ID help to balance between differences of conversion rates across advertisers and directly model the affinity of winners to them in general. Also, the kind of features you can use depends on the kind of architecture that you have. So some of the feature types and transformations might not work in an architecture if it doesn't support them in general. Next slide, please. So some of the challenges that we find in the production systems are that ads models are trained incrementally to capture feature distribution changes and also add inventory updates. However, due to storage cost limitations, training data set is always has some retention. This leads to an inherent bias between the production model and a new experimental model, as production models have been trained on more data in general. To overcome this challenge, there are multiple solutions, but here we share some learnings that we had. Since learned feature embeddings occupy the majority of learned parameters, we can warm start them from existing production models. However, we observe this technique works best when we have the same feature sets and only model architectures are being changed. Another standard technique in industry is to warm start and distill from production models. This technique works best in most scenarios. Also, we observe that moving to multitask learning with denser signals coming in from click and good clicks help to mitigate most of the problems as the model is able to warm start embeddings through the dense labels. Next slide, please. Let's now deep dive into the changing privacy landscape for such third-party conversion products. As the industry evolves, it is shifting to give more power to users to decide how their data is shared across platforms and control the flow based on their preferences. One such change happened for Apple iOS users since iOS 14 launch, which asked every app provider to explicitly seek permission from users if they wish to track them from third-party activity. Google Chrome Android are soon expected to provide such flexibility to users. Sorry. This leads to a major shift in the ads optimization industry. For users who opt out, ads marketplace won't be able to have insights, and this activity would be unobserved from their perspective. This thus requires a shift in how modeling works for offsite data in general. Next slide, please. Let's first understand how this impacts. Yeah, maybe Sam, can you click once more? Yeah, let's first understand how this impacts conversion optimization flow. This directly impacts the flow from third party to ad provider and making this activity unobservable both from a measurement perspective and also unavailable from a training purpose. Since a major population of users now become unobserved, it brings it unique challenges on how you measure effectiveness and also rank ads for these users. One standard way is to train you with users who provide you the data or observed users and utilize such models to infer for all of your population. You can clearly see that such a model would be less performant due to data domain differences in general. Next slide, please. Let's deep dive into some of the industry standard methods to deal with such privacy landscape changes. Let's assume we have a set of population where conversion labels are present for training, called as observed users, and the other set refers to unobserved users where we lack labels in general. We can break down the thought process into the following verticals. First, improving third-party performance by utilizing more of the first-party activity. As already discussed before, this can be achieved through better feature engineering, leveraging auxiliary on-site signals to improve performance. For conversion prediction in specific, we can leverage techniques of post-click feature distillations to further improve performance. I'll go more details in the next slide. These changes are also can be considered as a typical scenario of unlabeled training. That is, we do not have labels for some domain, but you want to learn better predictions for them. For this, we can leverage ideas from pseudo labeling and semi-supervised learning to build better models. Thirdly, since labels are more sparser than before, it is important to invest in techniques that deal effectively sparser data, specifically around ensemble model techniques and data augmentation. Lastly, given there's an inherent bias between the observed and unobserved distribution, it is important to leverage advancements in the field of domain adaptation and smarter sampling techniques to ensure training data is reflective of the serving population. Next slide, please. Yeah, so one important and strong technique to improve conversion prediction in general is privilege feature distillation, which was first proposed by Alibaba. The idea here is very simple. Post-click features such as hide, click, dwell time are important indicators of whether a conversion will happen or not on the advertiser platform. And thus these signals would help to predict conversion better. But note the problem with these features. These features are only computed after the user interacts with the ads. Hence wouldn't be available during the time the prediction is being made, making these features some kind of privileged feature. So these features, though indeed are helpful, can't be directly used to improve models. However, we can utilize distillation techniques to transfer this knowledge to another model, which doesn't rely on this privileged feature. The idea for distillation is very simple. We refer to the first model, let's say to be a teacher model, and then we guide another model which can be served but doesn't use these extra features, but the guidance is in a way that we want to learn a similar distribution, but by not relying on the features that cannot be served. Next slide, please. So this is like a very simple way how we can leverage the teacher models to also do like soft label distillations in general and unlabeled training. So here, let's assume that you have a teacher model that you have trained with your observed data where you have all the labels in general. Now, once you have trained these models in general, you can utilize these models to create synthetic data for your unobserved users in general. You can make inferences based on their on-site activity on the platform, and then regress your models against these labels in general and refer to them as soft labels through a student network. So one of the power that you can see here is that for these models which are making these synthetic labels, you can utilize the previous technique as discussed before around privileged features to develop much more powerful offline models in general that can infer your labels without relying on offsite activity for unobserved users, but are much more powerful because they are mostly heavily focused on your on-site activity in general. Next slide, please. The other motivation around it is to improve the domain adaptation across these two domains in general. And we can take idea from domain adversarial training research in particular. So let's assume in this graph in general, like the green part and the purple part is your generic model. You have feature extractor layers, you have your classifier layer on the top in general. So when you train a model in general on this with your observed data, like the model would learn mostly the distribution of your observed data. But now when you want to apply this model to unobserved data, if there's a feature distribution shift, the features that the model had learned earlier would not work well. So how can you now distinguish a model and create a model that doesn't have this feature distribution shift in general? One way is to use like the technique from domain adversarial training to add a different domain classifier task to your model in general. Now, this is like very similar to recent advancements in discriminative learning in general. So now you have two different objectives in your model that you're jointly optimizing. One is optimizing to minimize the prediction loss in general for your label predictor. The other task is trying to optimize for confusing the model, like it's not able to distinguish whether an example is from a domain A versus a domain B. So by training in this fashion, you can force your model to not be able to distinguish between two domains in general through the gradient reversal layer, and maximize your model performance to not be able to distinguish two domains, but still be able to be performant across your label prediction in general. Next slide, please. And lastly, differential privacy is another industry standard way of making models more private by default. So even if you don't consider the recent privacy challenge changes in general in the landscape, like we can still apply differential privacy methods to make models more private by default so that they don't remember an individual user in general. So the idea here is very simple. Like you take an individually identified user data in general, you apply some noise over it, you utilize differential private model training techniques to generate a model that doesn't remember the data uniquely in general. Differential privacy uses randomization to prevent privacy attacks. Differential privacy backs with theoretical proofs in general about a privacy of a model. The noise level of differential privacy is computed based on a privacy budget. Larger epsilon means that we have more privacy budget. I'll go into details into one of the technique in the next slide in general. Next slide, please. So label differential privacy applies the concept of differential privacy only to the labels in general. So you can now assume that, let's say in the context of conversion prediction, like for the users who have opted out, their labels are missing in general. Or also for users that, like for conversion prediction, the labels are the more controversial part in general. So what here you can do, you can introduce noise in your labels so that the model doesn't learn the labels directly. So the idea is very simple. Like based on your epsilon, you create a probability that you want to flip your label in general. Based on the probability of flipping, you will flip your one, like let's say if your label was that the user converted to be one, you will flip it back to, let's say, zero. And if the label was zero, you flip it back to one. Depending on epsilon, how much noise you add is controlled. So here, one thing that you can look into, let's say if you have epsilon one, which is a very high privacy budget, it means that you're adding a noise ratio of around 26%. A noise ratio of 26% means that 26% of labels have been flipped. Similarly, if you keep on increasing your epsilon, you're adding less noise in general. One of the challenges with adding differential privacy to the context of conversion rates is that conversion rate prediction is a very sparse signal. Now, let's say if you add more noise, and let's look into how the conversion rates change. So let's assume that conversion rate is around like 0.001 in general. So if you add noise in general, most of your samples are zeros, and those get converted to ones, which increase the conversion rate significantly. Now, when you add the noise, your estimated conversion rate in the data changes, which prevents your model to learn anything effective. So now the challenge is how can you control this noise when you add, with also satisfy the differential privacy constraints. Next slide, please. So Google has a very good blog in general to go over best practices. But if you want to understand like how we can handle these noise transitions better, there are three different directions in general. One is you can control the way we are adding the noise. One of the way that we showed earlier was the vanilla version. There are other advanced versions using Laplace formulations to add this noise. The other ways around like utilizing like Bayesian noise correction through like debiasing your data sets in general by utilizing public informations. Thirdly, it's important for your models to learn in this world where the labels are more noisier in general. And this can happen through introducing more auxiliary loss through robust losses, doing in-trainer pseudo labeling, and also gradient control. Next slide, please. Yeah, thanks for, and I also want to acknowledge like our collaborations in the entire company in general across different organizations to build performant convergent business in general. Next slide, please. I think that's all what I had today, but we can take some questions.
Yeah, Ayush, so there are, I think, some questions in the chat. I don't know if you want to.
Do you want to pull questions or? Or I can see one from Manish. Do you have any specific way to address the sparsity in the data you collect? I understand along with sparsity, the skewness in the label might also be quite high in such data. So I think the way we address sparsity in the data is through two different formats in general. Like if you look into the sparsity that arises between impression and clicks, like if you have 10K impressions, we only have like, let's say 100 clicks. The way we train our models is to downsample our negatives in general. So we do perform a negative downsampling so that we don't have that many negatives in the model in general. And also, it also reduces the dataset size in general so that you can train effectively. In terms of skewness, we do look at metrics across slices in general. And based on the slices, we do adjust our sampling strategies. I hope that answers your question. I think Yogesh has a question. When we say we use soft signal, such as user interaction in another model, how are we using in personalized recommendation? Yeah, so in terms of using soft signals, such as like soft signal distillations that we are doing in general, we utilize all of the users' on-site activity in general to understand what the label could be. And since we do it on large scale of users, like we average out the effect for a user in general. One thing that we do observe here is that the more we invest in on-site activities on Pinterest in general, the better rewards it provides us in general, because we know what the user is looking on Pinterest and we can better connect it with the user in that perspective. Does that answer your question?
There's one in Q&A tab by Akhil.
Okay. So have you experimented with casual uplift modeling techniques to identify the causal impact of certain features variable on the consumer journey stage and embed them in learning nonlinear dependencies? So I think that's a good question. We haven't invested in causal uplift modeling in terms of feature engineering in general. We are mostly looking at from like a label perspective, like to define like how good a label is in general. So label, even like a user might have different touch points on Pinterest in general, like different ways they might have interacted with an ad. Each of these touch points on Pinterest could also be attributed to a conversion. Like let's say if a conversion happens, each of these touch points could also be a potential positive label. Now, how do you handle this potential positive label? It's something where we use like uplift modeling in general. Yep. That's all I see in the Q&A right now. But yeah, I can answer more questions on the chat in general. Reply back to the chat. Yeah.
There's one by Yogesh.
Differential shift can also be done by covariance data shift. Like I'm not sure, Yogesh, what do you mean by differential shift here? Can you like clarify it more? In what context?
Yogesh, I've allowed you to talk, so maybe you can
Hey,
unmute and ask
hi,
the question.
Ayush. So
Yeah.
we talked about the differential property, right? On the data front, like let's say training data is something, and then the test data behavior changes, right? So
Yeah.
so that we are, I mean, using some differential technique, which I'm not sure right now. Like the PPT slide you showed. Can you just go back to the slide once? Go back. One more. Yeah, this slide. So here basically, right now you're using the domain knowledge, basically, or domain classifier something, to sort of bypass that change which we are expecting in the test data or maybe unobserved data, right? So
Yeah.
can it be done by this covariance data set where we kind of see that the property of data should retain whatever property we had in a training data should be there in a trace data. So suppose I'm saying one example, like the age group is there. Age group is like in training data is 20 to 30 somewhat. Okay. And suddenly in trace data, the age groups change to 60 to 70 on years basically. So the model was not capable to take those change in the age group. So that's the reason we kind of apply the data shift basically, which we call covariance shift, or maybe whatever we say deviation change basically. So can it be done by that way? The one you said, the gradient reversal layer.
Yeah, okay. Let me give more details of what's happening in gradient reversal layer first, and then I think I can take your question.
Yeah.
So the main motivation here for gradient reversal is, let's say you have features F that you're learning at this point, whichever the green line, the last green line is in general. So these feature F, we want it to be such that using this feature F, we cannot distinguish, like if we pass it to the red model, we should not be able to tell whether it's an observed user or an unobserved user. So at this point, this feature F in that particular case, like even that age group or not, but these feature Fs at this point after the feature extractor are indistinguishable for an observed or unobserved or the unobserved user in general.
Okay.
So these features have the same distribution, and thus when we pass it through your label class, that the purple box here in general, these features will be able to give you good predictions in general for your unobserved data. So one challenge here that you can see is that you're mostly making the model maybe better more for your unobserved data, the data that you don't observe. So in these particular scenarios, what you can typically do is have two different models. One model that works for unobserved data, having these gradient reversal layers in general, and one model that doesn't have it.
I think I got it.
Thank you.
Okay, I think in the interest of time, let's move on. Thank you so much, Ayush, for the presentation.
Thank you.
Okay, guys, we'll just take like 2 or 3 minutes break, bio break. We'll come back at 3 o'clock in just 5 minutes, 3 p.m. IST. And then we will continue with Kushal's presentation. So yeah, if you want to just bring tea, coffee, and take a bio break, please do and come back. Thank you. Hey, hi everyone. I hope most of you are back. Kushal, are you here?
Yes, Saran.
Hey, Kushal, I think you can go ahead.
Yeah. Okay. Hey guys, thanks for joining back from the break. So the topic we're talking about is challenges of developing effective and robust ad recommender systems. So the idea here is basically we want to cover some of the practical challenges which we have faced over by developing what the like time developing ad recommender systems at ShareChat and Moj. In no means this is be the exhaustive list, but yeah, these are some of the important ones which we have faced and think which will be helpful for everyone to understand and good takeaways for everyone. Yeah, next slide, sir. Okay, quickly talking about ShareChat ad. ShareChat ads is a common platform which is serving both the properties or the apps which we have, which is ShareChat and Moj. Rahul already briefly talked about the two apps. One is ShareChat, which has around 180 million monthly active users, and the other is Moj with 160 million monthly active users. The use cases of the apps are different, and they have like different challenges. Like ShareChat is a multi feed app wherein there are like different horizontal feeds which can be swiped up, and Moj is more a single feed video only app, right? We support multiple ad formats like videos, ads, banner ads, native ads. And also, again, this is not exhaustive list. There are more formats which we support. So that also is a consideration when we are building the ad recommender systems. Just like a point on the scale, right now, both apps combined are serving more than billion impression in at daily level. So that kind of, yeah, it's about the scale part. Yeah, next slide. Yeah, so this is the like outline. First, I'll be talking about the what stakeholders the platform is catering to, right? And also the delivery funnel overall at a high level, right? And then we will go into the ranker part of the delivery funnel, right? And then yeah, the challenges and like the idea is to explain the challenge, some of the solutions which are out there, which we have also tried, and give some pointers around those solutions which are out in open domain. The solutions or the pointers are not, again, exhaustive. It's not like a survey of all the solutions, but uh, all the milestone papers which or the milestones which have been there for that particular challenge is what I have tried to add in the slides. Right. So yeah, the challenges are basically around non-stationary data, data pipeline challenges, sparsity and dynamism in features, model divergence, and delayed signals. Yeah, that's what we'll be covering in this. Sarang, next slide, please. Okay. So coming to the the platform and the stakeholders, right? It's a three-dimensional problem wherein there are three stakeholders, right? If you see, there are advertisers who want to advertise on the platform and they have their own goals. There are users who are coming on the platform to basically consume some content and be engaged, right? And then there is platform which has its own goals, right? In the sense like at a platform level, we are looking for revenue, we are looking for diversity of ads, right? And again, the advertiser goals include like they should get say the match of the audience which they are looking for. There should be a brand safety in place and is in the and then whatever budgets they are putting, that should be utilized. And the most important is the ROI. Like they are mostly on the performance ads. ROI is the most important thing that advertisers are looking for. So yeah, and users basically, like if the ads are not relevant, users are going to churn, and there'll be high the problem of retention on the platform, right? So overall, these three stakeholders and the goal is to manage the expectations right here. Looking at like a little zoomed out version of the funnel, right? Starts with targeting. So whenever a user opens an app, right, and there's a request for a ad, the first thing which is done is kind of match the targeting in the sense demographic features like age, gender, location, language, right? So these are, every advertiser has their targeting goals, and each user has properties, and that matching is done. These are like some of them are deterministic. Some of the targetings which you do are also probabilistic. Like we have like support for lookalike audiences, wherein an advertiser can like seed a set of users and then create a lookalike audience and start targeting those. Right. Once the targeting filter is done, comes the stage of candidate generation. Right. So we all know, right, the recommender systems, like the ranker part is a heavy ML models which can't work at a scale of say beyond 10⁻³ or 10⁻⁴, right? So the candidate generation layer is the one which filters out all the candidates which come out of targeting and reduces it to 10⁻³ 10⁻⁴ ranges for the ranker to do the heavy part, right? So candidate generation layer is a combination of heuristics. This is general ranker flow. There's candidate generation parts, nothing specific to add, but like yeah, it is combination of heuristics and like ML based techniques, right? Then comes the ranker part, which comes up, which predicts the relevance of each user and ad combinations and emits the predictions for the auction and the pacing layer. Auction is the layer which kind of balances these expectations from advertiser, platform, and users, and also it takes inputs from rankers and other advertiser inputs, goals, and does the optimization to show the final ad to a user. Any questions at this point? Okay. I think this is a big question. Maybe, yeah, you can take this at a point, examples of different, yeah. So different ad formats, basically we have, as I said, video formats, image banners, which is like a static banner, and then like and then the native banners, which like goes well with the overall look and feel of the platform, right? So there are GIFs, there are different UI experiments, app updates which keep happening. So yeah, we support multiple ad formats then. Right. Yeah, this Devanjan, I'll come to the question in the last, maybe here. Right. So as we are basically talking about the RecSys challenge, right? This workshop is around that. So essentially in the RecSys challenge, what is happening is there is a training data which is given to all the participants, and they are trying to basically create a model which by doing all the feature engineering, by iterating on different models, right? And trying to bring out the best performance on the test data, right? That's the challenge, and that's how it is basically isolated from the whole system and is been given, right? And here, the expectation is the model will understand all the patterns in the training data and predicts the best output on training on the test data, right? Now, this slide, what we are trying is to make you understand like how it fits well with the overall system. So Sarang, just tap there. Next, yeah. So yeah, this is how the overall level view of the ranker looks like, right? And this is how the current RecSys problem fits into the system, right? So we have I'll quickly try to explain the ranker flow here, right? So the user is using some device, right? And the events is basically browsing through the ShareChat or Moj app, and there are events coming out of the user's phone, like add impressions, user actions like click, like, share, or also click out and landing to the landing page and doing installs or conversions or transactions, right? So all those actions basically go to a feature store, and that's where we do all the feature processing. We store all the user level, ad level, and all the combination features, right? And this is a small box here, but in general, it's a complex system overall, right? And how when the request flow is this, right? So when a user opens the app, a request goes to the relevance engine, right? And from the relevance engine, there is we have the predictions and auction layer, and based on that, the ad is served to the user. And again, this same events go to the training data, right? And there is a request log which is getting logged, and by joining the request and all the user actions is when it forms the training data. And this training data again feeds to the model, and then model gets updated to the relevance and the prediction engine. So this is a closed loop system which keeps running online, right? Next slide. Right now, coming to the challenges, right? So yeah, this is the section where basically I'll be covering challenges, the solutions, and the and some pointers for that, right? So the first practical challenge is data is non-stationary, right? The demand changes every time, right? There is a change of advertiser mix which is happening all the time. So there are advertisers who come in and go. There are long-running advertisers. The targetings change, right? And the creatives change, right? So the demand from the demand side, it's always changing. So that's one part of the non-stationary data. Supply also, basically the inventory which is on which we serve ads also is changing continuously. There are UI upgrades, there are app upgrades, there are additional removals of placements and creative templates, right? So that's the supply side change. There is impact because of the seasonality. Some advertiser categories having a very good engagement rates in festive seasons. In India specifically, there is IPL, there is Diwali, there is New Year. So yeah, multiple seasons, and there is seasonality impact, which changes the data patterns. It's sensitive to trends, right? There's some suddenly some trend starts, and then advertisers start creating creatives around that trend, and that also kind of change the whole data, right? So that all these factors contribute to the non-stationary data in the online world. And training a model offline once in a while makes the predictions stale and will definitely deteriorate the model over time. right? So there's a good survey paper, the whole concept drift thing, and yeah, like you can go ahead and look at it. That next slide, sorry. Right, so we understood the challenge. Now the solution is basically like quite intuitive, which is incremental training and online training. These are two solutions which are available. When I say incremental, it's at some frequency with some training data, model getting updated with new training data every time, right? So and the other part is online training, wherein we continuously keep updating the model in near real time. And yeah, there are pros and cons of both the systems, right? The first one, which is training incrementally at some frequency, is more robust compared to the online training. Online training is more susceptible to failures and less robust. The things which we have to keep in mind while doing incremental training is the hyperparameters have to be tuned specifically based on the frequency, right, and the training data sizes, right? So that has to be kept in mind. Also, that's the case with online training also. So this diagram is a simple representation of incremental training, how it happens in a real world system. So we have a training data, we train a model from scratch at T0, and then only the new data is used to update the existing model, and then that's the model at T1, right? And yeah, that's happens, so on and so forth. The challenge, again, there's one more challenge apart from the training, data preparation, and incremental training is updating the model in the prediction service, right? Because prediction service has to run all the time. So there are multiple ways, again, on that, to ship the model in batches, to ship the whole model. So yeah, again, the references for that are in the links, right? So you can go and look into it. Cool. The next challenge, like coming back to the ranker diagram, right, is on the data pipeline, right? In each stage of the ranker, because it's a closed loop system, right, there can be failures, right? So there can be failures or lags in the from feature store to prediction engine. There can be failures or lags from event processing to feature store, in event processing to training data, and also like training data going to models, right? So how does it impact? Like just basically give a glimpse of like each failure and how can it impact, right? So the first one is feature stored to the prediction engine, right? Suddenly, like there is a link to the feature store is broken, and say the counter features are not getting incremented anymore, right? So the distribution which is learned by the training data is not now same as the inference data, and like suddenly the predictions will definitely be not as expected, right? So for example, like a position is a feature wherein, like, normally there's a tendency, if we see more ads, there's ad fatigue, and as the number of ads, so we see more ads, the engagement rates decrease. Now if suddenly the number of ad counters incrementing gets stopped, right, and that's where, like, the predictions will always be higher. Like the engine will be for the engine, it's like first ad all the time, right? So that's a big challenge, right? Then the second kind of failure is events failure. Now events failure from user to training data or user to feature store, right? Again, like I'm talking one at a time. This can happen like all together also, right? So yeah, when there's a lag or error when events are flowing from user to feature store or the training data, this like our first challenge is like we don't have labels for the training data, right? Suddenly the engagement rates drop, and yeah, and what the correct training data is not the correct representation of the actual engagement rates, right? And yeah, that and what will happen is if we don't have corrective measurements in place, the whole engagement rates in models on the models will drop, right? And again, training, the third and fourth are kind of same, which is basically the logs getting delayed or the training data not reaching the model. It's the same problem of stale data and models not getting refreshed. So it's not basically not adapting to the recent trends, and the predictions which are coming out are basically used on stale data. So yeah, these are the challenges in the data pipeline, and yeah, there are ways to handle talking about. So Sarang, next slide, please. Right. So there are good amount of solutions both from like industry, academia, and also like some open source tools are available to handle this, right? So or like the gist of all the solutions is this: basically do a thorough data validation, monitoring, and alerts on the pipelines, right? Now the constructs here are declare the constraints, like what kind of constraints or expectations do you have on the data, right? And we can define these in terms of engagement rates, number of training samples. We can have like a lot of absolute constraints on the data, and also the relative constraints, in the sense for ID features, we can basically say that the count of per ID should not change like this, right? Or the distribution of a counter feature or a numerical feature should be within the difference between the distributions should be within this threshold. So all these are constraints which can be defined on some metrics, some aggregate metrics of features, engagement rates, and data, right? So basically compute metrics and apply these constraints on the matrix and analyze and report, right? And see the like the devil is in the details, but normally this is how it is done at a high level, and the errors are classified into like two high level buckets. One is errors which is like can't do training, or like or we have to say which can result in stopping the training, or it can also result in actually backtracking the model, and also warnings which just needs to be looked on and fixed and are not that serious, right? So yeah, there are papers around this, and I've linked them. Next slide. Right. So I think there was a question also around this in the chat sometime before. So this is also like this challenge is basically sparsity and dynamism in features, right? Since we have a lot of training data, we are basically operating at a high scale. We use a lot of sparse features, right? Which like gives us more efficiency, right? So we use features like user IDs or IDs, right? And by nature they are sparse, really sparse, and not just they are sparse, but they are dynamic, right? Then the users come and go. The hot users or the cold users also keep changing. So that's the dynamic part of it, and the sparsity part of it is basically there are too many, and we say on an average have say like not much data points for each user ID, add ID, right? And the traditional techniques, like having a big embedding table and doing a lookup, right, is a challenge, right, with Sparse, because say the users, as we know, right, are in millions, right? The MAU itself is in millions, and we need to maintain users for a longer time, right? So the user tables actually go in billions. So keeping a fixed embedding table is not like feasible, right? And there are challenges around it. So the solution is basically like the recommendation systems require the ability to capture numerous features and basically dynamically adjust the number of users and the ads they handle. And this is basically doing dynamic evictions, and basically users who are hot users, dynamically keep them in the models. Users who are cold users, remove them from the model. And to maintain a big embedding tables, there are techniques which can do collisionless hash tables, which has less memory footprint, and also are collisionless, right? So practically collisionless. So these are some solutions on the sparsity and dynamism of features. So there's a good paper on a tool available on this, which is Monolith. The previous studies on the sparsity and dynamism features was done by Facebook, so that link is also there. And yeah, you can go for it. Thanks. Yeah, next slide. The third challenge, which is again like it's significant, is on the model divergence. Model divergence is, since it's a closed loop system, we are training at regular frequencies, and it can diverge because of change in training data, and some of it is expected, but if there are real problems in training data, we can catch it at the data validation layer. But the model itself, because of multiple reasons, can diverge, right? And it can have underfitting, overfitting kind of problems. That that again is a real problem in the practical setting, because it will directly influence the relevance and overall end-to-end performance of the system, right? So for that, this is not a very deeply studied research problem, but yeah, this is more of a practical problem, and we have there are solutions around it, which we kind of have created over time. And high level can be categorized into two categories. One is pre-deployment validations, and then the second is post-deployment validation, or the model monitoring, right? The pre-deployment part is basically, as the name suggests, don't update the model before into the service, right? Do all the validations thoroughly and then push the model. So that is some of the techniques which are used normally is whatever new model we have received, right? Run the same model predictions on the older data, and then match the predictions with the older model, right? And that the deviation should be within threshold. So yeah, that's what is written in the bullets here, comparing the new model predictions on same data with baseline models, right? And also this is again a relative stats, and again there can be some absolute validations, like the performance metrics, like say ROC, AUC, or PR AUC, or normalized cross entropy. These should not go beyond a minimum threshold. Is when we make sure that data is ready to the model is ready to go into the service. The post deployment, I think that is normal, and it's basically running a continuous A/B test over long-term controls, right? To see any divergence. Then again, like perform the performance monitoring on the absolute scale on the like actual on the actual production data at daily level. Yeah, yes, next slide. Yeah, the last one is I think this was also covered. I'll basically give some practical examples on this. This is delayed signals, right? Delayed signals is more prominent in the ads setting, because ads, like a lot of user actions happen outside the platform, right? Like install, conversion, transaction, registrations, they happen outside the platform, and they like, yeah, they kind of, if we like, there's a trade-off in the sense we are trying to use the recent data as soon as possible, right? But we have to wait for delayed signals, right? So for example, like there's a say advertiser which is has a fashion is a fashion advertiser versus advertiser which is an electronics advertiser, right? Normally people are impulsive on fashion buying versus electronics buying, but say the conversion rate of electronics is higher. So if we don't incorporate delayed signals and just work on the immediate signals, the the relevance for fashion will come out higher, right? Which actually should be opposite, right? So the solutions in this space are basically this has been like this has been a long studied problem. The first solution which came out was in 2012 from Criteo, which was like have a separate model which only studies delays, right? In at for a given user advertiser, and then incorporate that into the final prediction model. More recent advancements are around like use the data with false negatives as soon as possible, right? And then whenever the delayed signal arrives, basically correct for the false negative by like unlearning and learning the model. So there are like multiple ways to do that, but the idea is use the record for training as soon as possible with false negative, and then yeah, correct it later. Yeah, I think, yeah, that's it. 4 times, so I can take questions. I can, yeah, go to the Q&A session. So it's very related not to RecSys in specific, but RecSys in general. If we query about RecSys as a system operating on similarity between user item, there are two somewhat interlinked problems with such a design. Okay, how do we address diversity? What is the extent of similarity to be considered? Yeah, like I kind of got the gist. So you're basically saying if we have user embeddings from somewhere and item embeddings from somewhere, and like have a similarity between them, and use that as a score, right? And yeah, I mean that's what in nutshell is happening, right? With just that in ads, it is like the signal is very sparse, right? So they need to have a lot of dense features in like to make the system more effective, like because there are a lot of like as I said, the data keeps changing. There are a lot of cold start requests which are coming in, so dense features help. But yeah, we essentially are using users and items and calculating the similarity using the models, right? How to address the diversity, right? So I mean, diversity, as I said, is desirable for the platform in general, right? Also for the user. So there are multiple ways it can be like solved at the ranking layer. It can be solved at the auction layer. So there are both type of solutions available, like in the sense, like do it based on the scores which come out of the relevance engine, and then have an overall optimization problem of revenue, relevance, and diversity, and also like can be incorporated in the ranking layer as an optimization constraint, right? I think I answered this question. So second is from Yogesh, candidate generation unique ads mapping to all users or vice versa or something else? Exactly. Yeah. So this is among the pool of all the ads which are available for a user after the targeting step. You kind of have to like filter ads for that particular user. Yeah, that's the candidate generation, and bring it into a scale where the final ranker can handle the scale. Right. So how are we solving the cold start here? I mean, so like there are ways to handle at feature level and also at model level, right? At feature level, having more dense features, right? On advertiser category level, right? And in general at user demographic level, help solving cold start. And also like doing like model level changes, model level optimizations, which is like having more regularized models, having like uh, not doing a lot of like tuning based on IDs. So yeah, that's we can handle at both levels. We are also doing the same. What kind of data drifts one can expect? I kind of like covered that in the whole slide of non-stationary data, right? There can be advertiser shifts, like new advertisers coming in. There is supply shifts. There is like shifts based on seasonality, based on right very recent viral trends. So yeah, these all actually translate at feature level. Yeah. Would we get a baseline to beat in this challenge? Do we get to submit only a single model? How can we see numbers for models from others? I think there is a leaderboard already. I'm not sure. So yeah, basically when you submit, you can go have a look at leaderboard, and you'll have your score, and you can like evaluate yourself with against others. Is there a limit on the model size? How do we know if a model can be used in prod and is not violating a latency thresholds? It's a very good question. Right now, like there is no limit on the model size, but keeping this practical challenge like thing in mind is really important. So yeah, models with less latencies will be encouraged, but right now there's no limit on the model size. I think the questions are on the RecSys challenge more, is it? What is the ground truth for your delayed signal captured? Okay, so so we like there has to be some ground truth, right? So we have like fixed ground truths based on the signals, right? So suppose a conversion or install has we kind of say like not go beyond 4 days, 7 days, right? And even there are signals like which have more delays intrinsically, like transactions, registrations. We have fixed a higher cap for them. So I'm on Michael's question. How many unique input variables are you approximately using for training your models? And how and when do you check if input is still makes sense? So unique features, I'm not sure, like exact number I can give it. But yeah, there are like a lot of features which we are using, and like we have like increased the number of features over time. And yeah, like a lot of all the ID based features definitely, and all the like interaction based features possible at all levels. I think this, yeah. So, Han, do we have time for more questions? Can I?
Yeah, maybe just take one more question and then we'll have to move.
Cool.
So Deepan, we will share the recording, definitely.
So I'll take question from Akhil. In a multi-stakeholder recommendation problem, can you please elaborate on how you are balancing the interest of advertiser versus end user and handling the long tail advertisers or users? Like, great question. Like the first part is a stakeholder recommendation problem, right? It is a multi stakeholder recommendation problem, and as I said, we are like handling it at different places, right? In the model and also in the auction layer. And this is uh, like we kind of optimize for all the like goals in a yeah, and then come up with the final rankings based on the input from rankings, based on the revenues. And yeah, we formulate it as a multi optimization problem, and then like finally come the final output is the combination of all. Right.
Okay, great. Thank you. Thank you so much. And I think we'll have to move on. So what are we going to do next is this. So there is a small quiz we have created for you. I would encourage everyone to go to Slido and do this. In the meanwhile, let me just open up the Slido board, but go to slido.com and key in 3164001. You can also scan the QR code if you're on mobile. If not, then go to slido.com and key in 3164001. And just give me a second. I'll open up the Slido board. Yeah, and yes, so we can already see a lot of you. I think around 13 people have joined. Please write your name or at least some identifier. Let's just say that. So again, slido.com 3164001. Yeah, I see 15. So we have around 35 participants. So I guess half of you have joined. I'll wait for others to join. It's going to be just quick quiz on some of the questions of AI, recommendation system, some content you already heard. So yeah, please chime in. I'll wait for 10 more seconds. And we'll give a Amazon voucher to the winner as well. Okay. let's start. So the first question is this. Okay. We have 23 people here. So just what are some of the challenges of measuring the accuracy of an ad recommendation system in the predictive model? The data is too often is noisy, the data is often sparse, the data is often imbalanced, or all of above. Right. So we'll move in 5, 4, 3, 2, 1. Next question. So, okay, most of you have voted for all of the above, and that's the right answer. Perfect. Okay. So obviously, this is a leaderboard as of now. We'll have the final leaderboard later. Here's the next question. I'll give you time to read through. This is a little more descriptive than others. Yeah, so please go ahead and vote for the right option. And just to tell you, we still have 2 more presentations. This is like a halfway through. Okay, we have 14 people voted in. Please vote for the right answer. The answer you feel is right. Okay, 16. Then we have all others to vote. 17. Great. Okay, we'll move in next 5, 4, 3, 2, 1. Okay, and yes, the first one is the right answer. And I guess half of you have got it. Okay, interesting. Now the competition is getting fierce. Let's move on to the third question. Which feature encoding technique can be used to transform categorical feature into numeric representation while considering the relationship between the feature and the target variable? And these are your options. Okay, this should be a quick one. Okay, we'll move on in next 5, 4, 3, 2, 1. Okay. Here we go. Most of you have voted for target encoding, and it is the right answer. So well done. Okay, here's how the leaderboard looks like. Manish is leading as of now. And it's how quickly you answer these questions also important. Here's the fourth question. Which normalized technique is commonly used for positive valued numerical features to handle skewness and compress large values. Okay, I hope you are voting. Okay, great. So we will close the poll in next 5, 4, 3, 2, 1. Okay, most of you have voted for log transformation, and it is the right answer. Okay, and here's the last question. The user cold start problem can be mitigated by creating features based on, again, how quickly you answer is also important, not just the right answer, but so yeah, it's important you do it quickly. Okay. Okay, we'll stop in next 5, 4, 3, 2, 1. And okay, the most of you voted for user demographics, and it is the right answer. So really happy to see most of you got all of the answers right. And here's the drum roll. Great, Yogesh Agrawal is the winner. Yogesh, congratulations. It would be good if you can just email me from your email ID, maybe the screenshot on sarangbrahme@sharechat.co. I'll put it in the chat box. But thank you so much, everyone. The hardest question was the ROC one, which a lot of you, again, 50% of you have got. So thank you so much. We'll stop the quiz now. And just 1 second, I will restart the presentation. Just give me 1 second. Chirag, over to you.
Sure. Hi, everyone. Once again, thanks for joining. I'll take a slight technical turn now. So essentially, Ayush had already motivated that multitask learning works quite well in practice across domains, but has seen a good sort of gain in ad system as well. So we'll try and go through the challenges, the benefits, and essentially how multitask learning can be extended on ad system. Let's proceed with that. Sarang, next, please. Quickly laying out the outline. So obviously, we'll start briefly with what multitask learning is. Very quick and a brief introduction of it. Although the theory of multitask learning is quite vast, but let's still deep dive into a few smaller aspects of what it tries to solve. What are the approaches there in the literature to address the same? And then let's bring the ad context there as to what all signals that we have in ads that can benefit from something like MTL multitask modeling, and once again, how it can be extended to various other additional signals that we have on our platform, and any other nuances that we have to keep in mind while we are modeling all of these things. Let's start with the introduction itself. As always, any new topic, let's start by answering some of the questions that we can around essentially what is multitask learning. So very intuitively, if you have figured out one particular signal, or you know how this can be learned, and you are struggling to model something new, and you know that the two signals are correlated with each other in some sense, try out multitask learning. It might work well out in practice, because you need to transfer some knowledge from the previous signal to the other unlearned signal. And that is what multitask learning tries to do. It stacks up all the signals that you want to train in parallel and tries to learn them together. wherever there is shared information that you can benefit from, the model figures out, and in process, essentially, what you hope is you get all the signals that you can learn from, learn that you would get at a better sort of accuracy instead of learning them separately. So this is something that is primed for ads as well, because in ads, we have various signals like click, install, conversion, deeper funnel, and so on. All of these are essentially trying to learn the same thing, wherein users affinity to a particular ads. And hence, it's kind of something that is applied beautifully here. Additionally, to motivate the benefits of multitask learning within ads system on the production side as well, it's quite difficult to manage individual models for click, install, and all of these things without multitask setup, because you can imagine any new feature that comes into the pipeline, you would have to test it out across the multiple models that you have. Additionally, all of these models, while serving, are maintained separately, have cost implications for them, get quite heavy in terms of their own inference side and things like that. So having a single model that can give all the signals, even at the same accuracy as individual towers, in itself a better idea. But modeling point of view as well, multitask just helps get the same signals at a better accuracy. So it makes sense to try multitask learning within ads, and which is what many people have done and have seen immense benefits from. So yes, Sarah, next time. Awesome. So let's start with some of the approaches that are there in literature, and I'll bucket the approaches into a couple of themes. So essentially, when we say we have to learn a few signals together, there is also a nuanced idea around how to share whatever information there is for one signal with the other signals. So sharing can happen in multiple ways. There can be quite simply hard sharing, wherein you have made the layers common for all of these signals. Beyond those common signals, you can learn them individually by having separate towers. But essentially, there is a set of common layers for learning all of these signals that you have in your model. That's in simplified version, hard sharing. But it need not be the thing that works well in practice, because you need some sort of flexibility to learn signal-specific signal-specific nuances around all of these individual things that you're trying to optimize. This is where further motivations around soft sharing can come in, wherein you want to regularize the sharing aspect of each of the models, wherein you you try to incentivize the model to learn the weights close to each other, but they need not be same. And that can be sort of incentivized by having just additional parameters around the loss function, which tries to minimize the distance between these two weight metrics for all of these individual signals. All of this sounds good, but there are further challenges in terms of how you can decide what all to share and how much to share. So all of these are kind of hyperparameters that someone can look to tune, but it suddenly, like you'll soon see that it kind of goes out of hand quite quickly, because as you keep increasing number of signals, the parameter space that you're dealing with also grows exponentially. And hence there was always a need to have a better sort of a system in place, for which many nuanced architectures have been defined. MMOE, which is multi-gate learning, is something that tries to solve it, and we'll have a deep dive into that in subsequent sort of slides. So this is one aspect or one theme of how multitask learning can be seen and the challenges within it. Secondly, if you imagine multiple signals learning together, you also have to be conscious of the fact that all of these signals have different distribution in some sense. And because of those different distributions or different baselines, the losses that each of these signals have can also be very different. So once again, contextualizing it in ad setup, if you try this out and see in practice, you'll see that because of the density of the data, the click signal has a lot more data compared to install signal. And hence the loss, just the pure CTR loss that you compute, say binary cross entropy loss for CTR, can be very high compared to CVR. In its vanilla form, if we go and train this model, it might turn out that because the entire model is trying to optimize on the total loss, in whichever way we aggregate, it might focus on the loss that has a higher absolute value compared to the lower absolute value ones. And hence there has to be a need to sort of tune the entire architecture such that the loss propagation happens a lot more equally, so that you're not just focused on one particular signal being learning better at the expense of others, but you collectively learn all of them, and hence you see a final improved outcome. So we'll once again touch upon each of these solutions in the subsequent slides. So yeah, Sarang, next one, please. So yeah, let's deep dive into parameter sharing once again, the first theme that we mentioned. So it obviously controls the extent to which you want to share the information across all of these individual tasks or individual signals that we are trying to model. So the question comes is the number of layers you want to share across all of these. So in a typical neural net setup, you would have some embedding layers for your categorical features. Then on top of that, you have all the additional layers that through which all the continuous and categorical features pass through. So how to choose to what extent or to what depth your towers should share? That is one question. And then within that as well, are we sharing it in the hard sharing way, or are we sharing it in the soft sharing way, wherein the first diagram that you see, that's the hard sharing 3-layered setup, wherein all the 3 layers are exactly same for all the tasks, and thereon the bifurcation happens. And in the second example that you are seeing, second diagram, you have some sort of a soft sharing mechanism, wherein there is some sort of a additional laws being added to each of these layers, where you incentivize the model to learn something, learn the weights that are similar for all of these, but not exactly same. So it just adds some additional degrees of freedom in your entire learning setup. So this is once again a hyperparameter as to how many layers to share, and should it be a hard sharing, should it be a soft sharing, and so on. Yes, Sarang, next one. So yeah, as I said, like if you start some small, this might be something that you can tune by trying out various sort of parameters, and this might be a solvable thing. But you'll soon see that as you keep on increasing the signals that you're trying to learn, this becomes NP hard, and like it's kind of going exponentially in terms of how many parameters you need to try. And even there, like starting with the intuition of what to set, you'll have to also see correlation between each of these signals, wherein one can imagine, yeah, CTR and CVR might be highly correlated. So the extent of sharing might be can also be very high, wherein you have a lot of layers that you're sharing. But then again, maybe CVR is a more noisy example than CTR. So having that extent, having a lot of layers being shared might mean that the CTR's performance is something that deteriorates. So all of these aspects around signal correlation, noise in the signals, then the dimensionality of the data that you have available, like with more dimensionality, obviously the entire training setup has a lot more hypotheses that it can try and sort of choose that works best for the data given. But if you constrain the model a lot, all of these hypotheses kind of naturally go down, and you want to have the model, give the model a lot more flexibility in some sense. So all of these combined makes it very difficult to come up with the right set of parameters. And this is where the research direction took a direction where we wanted to, like, they wanted to automate a lot more than what we have in the current setup. So we have a lot of architectures that came in order to solve for these things only. But once again, one that works quite well in practice from Google is multi-gate mixture of experts, MMOE. So I have a small diagram that tries to motivate what it's trying to do. So essentially, instead of having just shared layers, you create n number of experts. So all of these experts, as the name suggests, would try to learn something specific in terms of whatever attribute there is for an ad, for an user, or anything like that. And with these experts out there, the idea is to see, let the model figure out what combination of these experts should go into what towers, and how the towers can optimize their own sort of learning. So this is where the additional gate comes in. So this is the final version of sort of gated experts, which obviously took a lot more iterations. So, but in the final version, what happens is the gate is applied on all the signals that go from expert as into towers. So number of gate is equal to the towers, but the combinations obviously is expert into number of towers. So this way, there is a lot more flexibility to the entire multitask setup to learn tower specific signals, while also enabling shared learning, shared embedding space for better sort of outcome across towers. So MMO is something that that we have also tried, and it's quite common for folks to start with this particular setup. So yeah, Sarang, next one. So yeah, like till now we have been talking about the multitask learning setup in its generic sense, but let's try to apply it in the ads recommendation setup. We all know that ads doesn't stop at the recommendation level. You also have an auction layer where you have to come up with a bid score or bid value that can go with each of these ads. It obviously relies on all the signals that you have predicted on. So it can be a function of click, conversion, registration, transaction, and so on. And this, when it goes into the auction setup, is actually in sort of auction with various other similar looking functions, but with different signals going in. So Kushal already motivated in the left diagram that you're seeing, Kushal already motivated all the feed side of things, the ad side of things, candidate generation and ranking side of things. But look at the impression, like post impression, what happens. So like if an ad is supposed to be optimized for say a transaction, all the signals from click, conversion, deeper funnel, wherein registration will have to come into the bid equation. But there is also another ad that's just optimized for conversion or click going into the same setup. So it's very important to maintain the data distribution for all of these signals. If the baseline conversion score looks like 10%, it need not deviate a lot from that. And that becomes a very important aspect in multitask learning, because multitask learning happens with a union of all the data. It becomes especially challenging to ensure that the signals learn what they are supposed to, instead of having like shifting distributions, shifting code distribution, which will affect the bit side of things. So yes, next one. Right. So as I said, like we can optimize for all the signals going to the model from the very start, but it becomes very challenging. So let's take it very small, wherein we just want to include click and conversion into a single model and see how that can pan out. As it turns out, challenges just around click and conversion going together, if we are able to solve for that, a lot of it can actually scale for additional signals that you will eventually add into the setup. So let's start with click and conversion. There is an obvious benefit of doing multitask learning just for CVR as a signal, which Ayush also touched upon. But specifically talking about the problems that CVR data faces, what CVR models are usually trained on is post-click data. So the click has happened, you take that data, and then you train your model. But on the serving side, that serving, during the serving, you don't know the click is going to happen, obviously. So the serving happens on the impression level data. So there is an inherent sample selection bias that sort of is there in the system when we train conversion models. Having a multitask setup where I'm saying my training would actually happen on impression data naturally solves for that. That's one benefit of having, additional benefit of having multitask learning within ad setup. Secondly, conversion models are also known for additional data sparsity. You have a lot less signals in the conversion setup. And hence, again, having transfer learning from click to conversion side helps a lot in terms of how the model actually performs in the online practice. So in terms of how it actually works, there is a nice paper around that's called ESMM, Entire Space Multitask Modeling. This is the diagram for that paper only. You can imagine if the core signal that you're focusing on is CVR, then CTR is essentially trying to act as an auxiliary task that you use to learn CVR better, which is what the first, the green tower is around. Within that, if you notice, what we are trying to learn is obviously two signals, hence the losses would be sum of two of them. but the other signal is not directly CVR. And that is that actually touches upon the previous distribution problem that I mentioned. We have to ensure that the CVR value is still a post-click CVR, because that is what goes into the bid equation. In bid equation, we usually have CTR into CVR as one of the parameter or a factor. If in that case, CVR is not a post-click CVR, the equation will go for a toss and you will be undervaluing a lot. And hence, to model the CVR still at post-click, there has to be additional modifications that has to go in instead of learning it directly. If you learn it directly, you can imagine the values that you'll get would be impression to install and not post-click install, which is click to install as a value. So this is where the paper talks about introducing a new signal, which is CTCVR. In essence, CTCVR is quite simply CTR into CVR only, but we don't learn CVR separately. CVR is assumed to be learned in the back propagation of combined losses of CTR and CTCVR. I'll urge you to read this paper. It's quite helpful to understand how the entire setup actually works for click and conversion. Yes, Sarang, next one. It seems like this was relatively easy to solve, but it's not quite the case. So once again, if you look at the second diagram and within that the second Venn diagram, we know that post-click conversion is a standard thing, but in practice, that's not the only thing. What happens is there is a good chunk of conversion that can actually happen without the click as well. So imagine a scrollable video feed kind of a setup. It's quite likely that the user, even if the ad is something that is engaging to the user, might not click right away. The user has registered the ad for the application. He thinks it's relevant, but in the session directly, there might not be a click. What would happen is user might go out of the session and install it separately. So that becomes a view through install, which happened due to the same ad that the user saw, but it was not preceded by the click. And this is also something that has to be modeled by the entire setup, because they form a good chunk of all the conversions that happen across many platforms, and specifically feed kind of a setup. So in the previous diagram that we saw, which was solving for CVR using post-click CT-CVR equation, view through install was entirely neglected. How do you how can we actually plan for including view through install separately into the entire setup? Should it be a separate tower in itself? Should it mean that the CT-CVR equation that we came up with needs some refining to actually support view through installs? That becomes a very important question to solve. Otherwise, these models are actually not applicable in practice. If you extend the same notion further, by what further happens due to presence of view through install is there is some additional noise in the relationship that CTR and CVR actually has. So CVR that we compute is on the overall install level, and hence it might turn out that there is not exactly positive correlation between CTR and CVR, and that raises a question on the shared space that these signals have. So is there additional tuning that is needed to further sort of improve the learning of these models, is something that remains a question, and we kind of try to solve for. So as I said, the additional thing that the third thing that I called out here is something that I previously talked about. CTR and CVR losses are something that are very off in terms of scale. One can be at e power -5, other can be at e power -10. So there is an exponential difference between these losses, and it becomes very important to weigh them properly so that the balance is actually maintained, which is an additional challenge that comes with solving for CTR and CVR together. Yes, Sarah. Right. So we have already looked at how to solve CTR and CVR, but as I said, things can extend a lot more from here. If we are comfortable with CTR and CVR modeling together, there is nothing stopping us from adding more signals from, say, registration standpoint or a transaction standpoint or things like that. But with more dependent signals being added into the system, the challenges that we have already discussed are in some sense sorted, but there are some additional challenges that come in, and we'll quickly go through those as well. we have been talking about delays in the signal feedback for some time now, and it is actually very important to model properly. Install delays are still in some sense manageable because that's a relatively smaller window. But if you look to add things like registration, the registration can take a good 7 to 10 days to actually come into the system. And if we are looking to model all of these together, one tower having a lot sparser and rather a noisy target input can impact all of the other towers as well. So how to solve for delays, not just in single tower setup, but additionally in additionally in multi-tower setup becomes very important. And once again, there are many studies around this that are still ongoing, and some of the resources I have linked later. But this is also very sort of an open topic to solve for. Secondly, sparsity to some extent for conversion was all right, but registration, transaction, deposit, all of these are very sparse signals. Like they happen at least an impression level. They don't happen frequently, and it's harder to train these models together collectively because the losses actually go very small at impression level. So the loss combination itself becomes very sort of non-trivial, and simple weighting doesn't solve for it. Once again, in theory, there are solutions around using gradient as a way to sort of choose which tower the losses should focus on. But still, that's something that I guess warrants a lot more research around. But yeah, this is something that one has to take care in take special care of. In terms of auction side of things, as I said earlier, it becomes very important to ensure the score distribution remains same. Why that is especially important is there is a calibration layer that goes on top of auction to ensure that across all the sort of objectives that an ad has, all of these are actually well calibrated so that they are properly compared against each other, and we don't bias the system towards a particular objective criteria. And hence the calibration side of things, for it to continue working properly, the modeling side of things has to give a correct the correct score distribution, and the trueness to the concept of post-click install or post-install registration continues to remain. That becomes a very important thing to ensure. So yeah, Sarang, next one. Right, so we talked about dependent signals till now, but as a platform imagining a platform like ShareChat, which is also a social media feed, where there you're not just tracking primary signals around CTR and CVR, you're also getting a lot of information about the user on how they interact on the application in terms of signals like what's their usual session duration like, what are the things that they usually like, share, comment, and so on. So all of these activity that they make on the platform, they are also something that can go into the model, and there is active research around how to sort of lay it out, because these auxiliary signals are not something that we need to sort of maintain all of these hygiene related things that I called out, wherein the distribution remains same, they themselves are being modeled properly in terms of giving us gains and all. But we also need to ensure that we are not burdening our system in the way that we have a lot of signals to properly model, and this becomes a very bloated model to actually maintain in practice. So their entire sort of framework around say Occam's razor can come in, wherein is there a better way to ensure that we have the correct signals into the model that actually help the primary signals without bloating the entire system? And is there a right way to approach that setup, wherein is aberration study the right thing to do, wherein you put in some signals and try to see what the outcome is, and then keep removing them and measure the impact or deterioration that the model sees. To start with as well, what are the auxiliary signals that should go into the model? So there must be a suite of EDA related offline EDA that we can do to come with a list of auxiliary signals that go into the model. So once again, this is a very active research within ShareChat as well, as to see the set of features that set of targets that we can sort of stack up on top of say MMOE buckets, and try to learn them all together and see the impact that we can get on the primary signals that we are concerned about. So hopefully I've motivated what multitask learning in general looks like and what is the setup for that in ShareChat. In the next slide, I mostly have references in terms of some good starting points to get used to what multitask looks like, as well as how it has been practiced in ad setup. Couple of papers around MMOA and ESMM were more seminal and have seen a lot of sort of adoption across industry. So once again, would encourage you guys to try and go through these whenever times suited. So yeah, I'll pause here. This was the yep.
I think there's a question. Kushal, if you can take.
Sure. How is multitask learning better than transfer learning in achieving better accuracy? MTL tries to make weights for different tasks with one another. Why can't we transfer model? So transfer learning is a perfectly viable option, which obviously people have done. But the thing with MTL multitask learning setup is you get additional flexibility in terms of what all features you need to share. Like you imagine you have a data set, you have 10 different hypotheses on how that data can explain the target. Even for the click signal, if you learn standalone, it can actually benefit from the conversion signal being together, because it's obviously better to pick one hypothesis that explains 5 different things than picking something that is specific to click. So learning click first, using that model to learn conversion later is a possible solution. But I would imagine that learning both of them together would lead to a better sort of a hypothesis space being learned, because that's something that is answering both the related signals together.
Okay, in the interest of time, let's move on. Thank you so much, Kushal. We'll obviously come back to some of these questions after the last session. So, Shubham, over to you.
Hi everyone, this is Shubham. So I'm going to talk about features in ad recommendation system. So I'll be touching upon types of features, feature engineering techniques, feature reduction techniques, and then move to some of the challenges that we face in production to maintain features at ShareChat. And hopefully some of these things can directly help you in the RecSys challenge as well. Yeah. So at ShareChat ads team, our goal is to cater needs of users and advertisers alike. So from a user's perspective, our focus is on presenting ads that are relevant to their interests. And introducing them to new products that possibly align with their preferences. So from advertisers' perspective, our focus is on increasing their visibility and connecting them to their target audience. So in order to do this, we need to know the intent of ad and the preference of the user, which is acquired through users' interaction and activities on the platform. Next slide, please. So, yeah. So coming to feature types. So features are the way we communicate ad intents and user preferences to our ML model, so that they can predict probability of click, install, or a deeper funnel event like sign up and purchase. So when designing features, our approach is to incorporate information about users, advertisers, and the surrounding context. So if we look at user, we have things like user ID, age, gender, city, and state. And if we look at advertiser, we have things like advertiser ID, campaign ID, creative ID, and advertiser category. So advertiser category can be things like food, clothing, fitness, and so on. Yeah. And yeah, coming to context. So context tells us where this interaction is happening. So things like feed placement, was it a video suggestion feed? Was it trending feed? And what was the time of the interaction? So things like hour of the day of the week, month, and so on. And also we also look at device information. So things like manufacturer, telecom operator, and network speed. Yeah. Next slide. Okay. So far we have discussed about user ads and context level features, which capture broader characteristics of the interaction. So now it's also necessary to capture interactions between the three to help the model understand personalized. Just a minute. Yeah, sorry. So yeah, it's also necessary to capture interactions between the three to help model understand personalized preferences and add intent at a granular level. So to do this, we usually combine user signals from 2 or 3 of them along with the actions. So here, if you see the example, we have combined user advertiser category clicks. So by doing this, you can imagine a feature like at a user level, we can have their clicks in, let's say, food category, or let's say clicks in clothing category. Yeah, next slide, please. Okay. So once we have created features, the next step is to transform them into something meaningful, which our models can consume. So in this slide, we'll explore various feature engineering techniques. So we have things like label encoding, one-hot encoding, and so where we take our feature and transform them into numerical values. So in label encoding, we are basically picking up a feature, assigning it a number. So you can imagine user city type feature where we have things like metro, urban, rural, and we are transferring them into 0, 1, and 2, like numerical values, so that we can feed it to the model. Cool. So going to one-hot encoding. So in one-hot encoding, we take the like feature and transfer them into binary vectors. So we have things like, so if you have a feature on ad type, so which can be video ad, image ad, or interstitial ad, we transform them into a binary vector indicating presence or absence of that particular thing. So for video ad, it can be 100, image, it can be 010, interstitial can be 001, and so on. Cool. So next we have target encoding. So previous one, yeah. Previous one, sorry. Yeah. So in target encoding, it has been found to work very well on tabular datasets. So in this encoding, feature value of a category is assigned as a mean of target variable of that category. So if we have features on, let's say, device manufacturer, so here we have Samsung, Sony, and Apple. And the model that we are training is a CTR model. So we have bunch of ad views and there are ad clicks. So we take the mean of the labels. So in this case, it would be 0.3 for Samsung, 0.2 for Sony, and 0.4 for Apple. And at inference time, the categories are assigned the feature values on the basis of what we got at training. So like you can find these techniques to be followed in multiple challenges as well as in multiple companies. So yeah. Next slide. Cool. So moving on to embeddings. Embedding lookup table technique is where each category is represented by a low dimensional vector. So these embeddings are learned during training, and they work very well in capturing inherent relationships and similarity between categories. So here you can see we have embeddings on advertiser category and food and drink. So for food and drink, we have a 64 size vector. And essentially what we want to figure out is we want to for this category, we want to train this embedding. And this is done along with the the model training part. Next slide, please. So all right, so far we have covered categorical features. Now we'll see how to feature engineer numerical features. So we'll start with basic scaling techniques first. So if you're using a tree-based model like decision tree, random forest, or XGBoost, so you don't have to worry about the scale of numerical features. However, for neural nets, it becomes important to scale your data. So to perform scaling, we have techniques like min-max, z-score, and log normalization. So now the decision to choose these techniques can be done on the basis of distribution of features. So for Gaussian-like features, I would choose z-score over min-max, and for a right-skewed positive feature, I would use log transformation. Yeah. Another technique that we use that we can use is binning. So if you believe there's a range of features that are behaving similarly, you can try binning them together. So here we have bin or bucketized age range features, age in years to age range. So we have 4 buckets created, as you can see. And then there's this extension of binning, and we have seen this perform very well in neural nets, very well in neural networks, in the tabular data neural networks. And in this technique, we create quantiles of feature values. So, and these bins are formed on the basis of quantiles. So here we start with some number of quantiles. So let's say 20 or 10, and then these quantiles are formed on the training set first, and then at the transformation step, we see the quantile of the feature and then map it to them. So here you can see X is mapped to I-1 over N-1, where I is the quantile of X and N is the chosen quantiles. Good. So in practice, we observe that features are not always present. So we need a way to impute them. So some of the basic techniques are mean, median, zero imputation, which work reasonably well if your missing features are less in number. So in case the missing features are high, sometimes we also predict missing features using another model. So obviously this comes with the overhead of maintaining a separate model. So this is usually done in cases when the features are of high importance. Next slide, please. Next slide, Sarah. Yeah. Moving on to feature selection and dimensionality reduction. So in practice, as we gather and create a lot of features for our model, we run into problems like overfitting, high compute and storage cost, maintenance overhead, and so on. So it becomes important to reduce the number of features and keep only relevant aspects of the data. So, so for this, we have techniques like correlation basis on feature selection, correlation-based feature selection, where we compute the correlation of input feature with the target variable and select most relevant feature based on correlation threshold. So this is especially useful when you have a bunch of features that you want to add to the model, and like you want to quickly start with some of the features which are high in importance. So the next technique is backward elimination. So here you start with all the features and start to kind of remove the least important feature at each step. Next is XGBoost feature importance. Like XGB offers various techniques like there's inbuilt feature importance, which and then there is permutation importance. And then there's SHAP values. So you can use any of these techniques to do feature importance and then do feature selection. Then we have like techniques like PCA and autoencoder. So where you like train a different model on features directly. So in PCA is basically principal component analysis, where where you find the top principal components, and then we have autoencoders. So in autoencoders, you try to learn a lower dimensional representation of your features. So, and then use that bottleneck layer as an input to the model. Next slide, please. So now we'll discuss about various aspects of handling features at scale and some of the challenges working with large data sets and numerous features. So first, one of them is high cardinality. So our models have categorical features like user ID, which has cardinality of hundreds of millions of users. So here, like we'll have to think about, because this would become very sparse feature if we, let's say, talk about encoding them in one hot. So, and even if we maintain embedding tables, storing them and then serving them would be a challenge. So second is feature correlation. So as we have discussed in previous slides, as the number of features grow, they add to storage, compute, and latency. So it becomes important to keep the size of features in check, which can be done by various feature selection and dimensionality reduction techniques. Next slide. Next slide, Sarah. Yeah. So in ads, as like previously pointed out, we observe temporal changes in user behavior. So it can happen due to a new trend in the market or a festival season, and like multiple things can happen. So to capture this effect, we also create various rolling window count aggregates. So things like user add views in, let's say, food category in last 1 hour. User clicks in food category in last 1 hour. So these features help us capture the recent trends that are happening in the market, and so that the model can utilize them and pick them up while predicting. So we kind of extend this to even further, where we calculate these temporal dynamics at a minute level or a 5-minute level. So this is done at runtime, where where we do near real-time computations of these features and then feed it to the model. Yeah, another challenge that we face in production is that at inference time, we would need all the features to be calculated, transformed, and then fed to the model as the user scrolls their feed. So we need to adapt and update the features continuously. So if there are feature read failures or delays in transformation, there's a mismatch in inference and training features. So it becomes important to make sure that there's a parity between the two. So to avoid mismatches, we do continuous monitoring that I'll be discussing later. Yeah. Next slide, please. Yeah, another very interesting challenge which we have already talked about is cold start problem. So as new users and advertisers sign up, there is a challenge to make accurate predictions using limited or no historical features. So now there are various model side techniques that we can leverage. So from features perspective, we can depend upon auxiliary information like demographic based aggregated signals. So here you can see we have age cross advertiser category clicks, which can be used as which can be used in situation when we have a cold start user. Next slide, please. Monitoring. So in production, monitoring feature pipelines becomes important because we want to ensure the quality of predictions. So because of the temporal nature of user behavior, we know that features can drift over time. We need to continuously track their distributions. So this involves doing various statistical tests and then doing distance metrics like KL divergence, JS divergence, and observing point summaries like mean, variance, and skewness from the expected values. So we do that continuously and then have alerts set up for them. So coming to feature quality, this again requires us to continuously monitor for anomalies, outliers, and any inconsistencies in the inference training feature computations. So some of the methods like observing what is happening at inference time and what is happening at training time regularly can help mitigate this situations. Yeah, next slide. Yeah, that was all from my side. If you have any questions, I'm happy to take them.
Yeah, thank you so much there. So I think we have 3 or 4 questions in the Q&A. I would invite all the panelists to check these and see if anyone of you want to answer these questions. Is done. Let me check. Okay, I think we have most.
Yeah, sir, most of them are answered.
Yeah, most of them have answered. I don't know whether these two are for RecSys challenge or not.
I think yeah, first one was also answered. Like if Rahul has to add anything on.
Okay, this is answered. Okay.
The model size and not violating the latency thresholds.
Okay, and this one?
Rahul, you're on mute.
Rahul, do you want to answer this?
This one. So do you anyway preserve the privacy the users in the data you collect and use, or do you model at user level? Okay, so what we do is that we do preserve the privacy of the user, and basically what happens, right? The privacy is at like privacy of a user is a multi kind of aspect of it, right? So number one is that all the data is obviously stored in a encrypted form and so on, and hashed and so on, so that there is no security breach that can happen from our side. Number two, we also drop a lot of what you call as features for which is very PII kind of thing. So we don't store them for long term and so on. Like it's not that we are storing something. ShareChat has also enabled the data delete kind of protocol, which is a user can actually say that I don't want to be tracked or I don't want to be monitored and so on. So those things are also there. And then obviously, like as industry is evolving towards privacy preserving things. So hopefully by next year, even the GIDs, which is like Google advertising IDs, those will also vanish away. So after, like, we're also actively working towards having solutions where we don't need to have GIDs. So yeah, like at multiple stages, we do try to preserve the we do preserve the privacy of the user.
Okay, great. Thank you so much. So I think with this, we are kind of nearing the end of this workshop. As we mentioned, I think we've got really a lot of good questions, and thank you so much for everyone for finding the best question. So we have shortlisted 3 questions, or 3 folks who have answered the best question, shared the questions. First one is Debanjan Das. So congratulations, Debanjan. Second one is Akhil Sakhardande. So congratulations, Akhil. And third one is a person with name Zuzu. So again, congratulations to you as well. We have your email addresses, so we will share the Amazon voucher there. Just give us a few weeks to arrange it. And yeah, I just want to recall the challenge that RecSys challenge is still going on. If you can go to ShareChat's website, sharechat.com/RecSys, the challenge is still there. And with that, I would like to thank all the presenters, Rahul, Shubham, Chirag, Kushal, and Ayush, for enlightening us with the Ads AI recommendation system content. We will be putting this on ShareChat's YouTube. After this, next week, we will also share an email with all of you with a short survey. We do want to do more such workshops for the AI community. So yeah, please let us know what else you want to kind of, see the content. And with that, yeah, thank you so much, everyone. I don't know, Rahul, if you want to say any last kind of.
I think it was an awesome audience. Like, and I think like I'm really thankful to everybody that they actually spared time on a weekend, and also like thanks to all the speakers. So I think everybody like this, like they had a very good content, and I think it was very enlightening. And I think the 4 speakers actually pulled together a lot of content in like I think 2 hours. So that was 2 or 3 hours. So that's actually again great. And yeah, thank you so much, Sarang, for organizing all these things. I think the logistics is always nightmare on doing all these events online. So thank you so much for putting up together. Yeah. And thanks for all the good questions. I think every question forces us to think back, like it's a good thing. Amazing interaction.
Absolutely. Thank you so much, everyone. I hope you have a nice weekend. And yeah, see you soon. Thank you.
Bye-bye.